All right, again, 110 is still rational functions, but it's rational functions with holes. So how does a hole occur in a graph? And it occurs if the fraction can be simplified by canceling out a factor in the denominator. And if it's the only of that factor, then it will literally eliminate the vertical asymptote at that point, and instead it gets a hole. So to find the coordinates of the hole, you'll take whatever the x is that you crossed out, and you plug it back into the simplified fraction. So that's important. We don't plug it back into the original. We plug it back into the simplified fraction to find the corresponding y. That will eliminate the vertical asymptote at that factor, again, unless the multiplicity is higher in the denominator. So I'll show you that in a second. And you will not see a hole on your calculator. So if you do if you use the graphing calculator to graph it, you have to be smarter than your graphing calculator, okay? You have to know that the hole is there. You will see the graph of the simplified fraction as though they did cancel out that term, but you will not see the actual hole, okay? In the table, you would see undefined for that point, but you won't see a hole in your graph. So what does this look like? This would be like if I had x plus 3 times, or over x plus 3 times x minus 3, let's say, for example. So this would cancel, and it like leaves you with a simplified graph, and that's what you would graph. It also takes away this vertical asymptote, which would have been x equals negative 3, and that's the x coordinate of your hole. Then to find the y, you would plug it back into your updated or simplified function, and I'd get 1 over negative 3 minus 3, which is 1 over negative 6. And there would be a hole in the graph at that point. So you would either draw your curve. Sometimes this might even result in a line instead of a curve, but at that coordinate point, it will be an open dot. Let's say, so what this means, unless the multiplicity is higher, this means, let's say it said x plus 3, and in my denominator, I had x plus 3 times x plus 3. There were 2 of them. I'm only going to cancel out one of them. So it would stay as 1 over x plus 3. And that means there's still a vertical asymptote there. Does that make sense? Okay. Not a hole, a vertical asymptote. All right, so this is what they look like, okay? Obviously, you've got your graph. There appears to be a vertical asymptote there. There appears to be a horizontal asymptote. We can't see exactly where it is, but they appear to be there. So if it gave you a graph and it asked you to identify the hole, you literally look for the hole in your graph and give the coordinate points of that hole. So the hole is at 3, 1 in this case. And then you're going to use limit notation to talk about what's happening at that hole. So if you look at that limit notation, it says as x approaches 3 from the left, right? Because that's what the minus is. So we're talking about as we get closer to 3 from the left, f of x, which is your y, what's happening to my y? Where would y be at 3? 1. So as we get closer to 3 from the left, the f of x limit would be 1. It's the y coordinate of your hole. It never actually hits 1, so it's just getting closer to 1, which is why that's the limit. As the graph is getting or approaching positive 3 from the right, what's happening to that y value? It's also approaching 1, so 1 is the limit. So if you are finding the limits of your hole, it's the y coordinate of that hole. So as x approaches 3 from the left, the f of x approaches 1. As x approaches 3 from the right, the f of x approaches 1. Questions so far? God bless you. All right, example 1 says find the holes of the rational function if one exists, and then use limit notation to state that hole. So first thing you're going to do, and now you have to do it with every single rational function. You have to assume that any of these rational functions could have holes. Okay, so if you go, and this is what was weird about these couple of sections is that there was holes. Like, I don't know if you saw, but like I edited your note yesterday. I like rewrote over some of your questions because they had holes in them. So I don't know why they had stuff with holes. Even like the classroom, that's why we're saving it for Monday, had examples with holes before we talked about holes. So I saved it for Monday. So now you're looping it all together. Very first thing you're going to do every time is factor and see if you can cancel and see if it results in a hole. So if I take the 10 out of the top, it'd be x plus 3. And in the bottom, this would be x plus 3 and x minus 2. So is there a hole here? Yes, because I can cancel out the x plus 3's. The simplified graph, or what I would graph if I was to graph it, and what I will find my vertical asymptote and everything from after this, would come from my simplified fraction. The only thing that comes before that is your domain. So when we start doing domain, we do domain first. Then we cancel, and then we find everything else. But this just asks for the hole. So is there a hole? Yes, there was only one of those terms. My hole, the x-coordinate of my hole would be at where? -3. And then to find the y-coordinate, I'm literally plugging -3 into the simplified one. -3 minus 2, 10 over -5, which is -2. With me so far? Good. Then I do the limit. Limit as x approaches the x value of my hole, which means -3 from the left, and the limit as x approaches -3 from the right. As it approaches both, right, from the left or the right, my y value is going to be -2. Good? All right, example 2, same thing. You do it. Actually, I'll do this one with you. Because what's the top?
It's a cube.
It's a perfect cube. Do you remember SOAP?
UV.
Huh? Oh, UV. Like the variables that are on that slide. Yes. Okay. We call it SOAP for short. Same, opposite, always positive. Does that sound familiar? Yeah, okay. So the trick to factoring perfect cubes is to cube root each of these terms. So this would be x and this would be 5. And then the first parenthesis is those two. We're going to come back in and fill in the signs. Those two, the x goes in the first spot, the 5 goes in the next spot. Then the square of the first one, the product of the two, and the square of the second one. And then we call it SOAP because the signs are same, which means it would be minus, opposite, which means it would be plus, and always positive is always positive. Do you remember that? Mm-hmm. Yes? Okay. So a cube could show up anywhere. You got to be prepared for it. And now this is over x minus 5. So is there a hole?
Yes.
Yes. What's the x value of my hole?
5.
Good. Now to find the y value, I got to plug it in. So 5 squared plus 5 times 5 plus 25. Which is 75. So my limit notation, the limit of my graph as x approaches 5 from the left, and the limit of my graph as x approaches 5 from the right, f of x equals what? Good.
Do we? How do we like? What's the point of putting the plus and minus signs? If it's always going to be the same for both.
It's the same for a whole, but it's not the same. Think about your vertical asymptotes. It wasn't the same for the vertical asymptotes.
Well, like when we're writing it for a whole, it'd be okay to write plus and minus signs. But
It will separate it out. Yeah, so a question like this, well, not on your quiz it would be open-ended, but like on a test, it would probably make multiple choice and they will put both. So, they throw in there an infinity to throw you off. They'll throw in there a 5 to throw you off, but they are the same.
so you can, instead of writing both of them, you can just write as x approaches 5.
No, because that's not the limit. You can't say, a limit has to have direction. unless it's infinity or negative infinity, because then it's those are two different spots. Does that make sense? Yeah, okay. All right, so this one goes back to the calculator. It says complete the table and then answer the following. So we fill it in. I will tell you this, that your quiz next week is not calculator at all. So like you won't have tables, but not on the quiz, but on the test, we're bringing back in the calculator. It's just easier to not have to go calculator part, non-calculator part, because you can't have it for the graphs. So test, we'll split it up. But quiz, I just kept it all no calculator. Wednesday. All right, so x squared minus 16 over x minus 4. I'm going to do y1 of 3.9. And then I'm going to do y1 of 3.99. And then y1 of 3.99. y1 of 4. What do we think is going to happen at 4? It's not going to work, which means undefined, right? Because if I factored the top, I'd get x plus 4 and x minus 4 over x minus 4. So that would be your whole. Y of 4.001, 8.001, y of 4.01, 8.01, and y of 4.1, 8.1. So the x coordinate of my whole is what? 4. The y I would plug back in here. So 4 plus 4 is 8. Good. And then look at my graph. What happened as it kept going closer to that hole? It gets closer to 8, right? Or my chart. Sorry, not my graph. Does that make sense? So again, I think you'll see these without the function. So you would have to know to read this chart that the hole is at 4 and that the value, these are both meeting at, is 8. So you'd have to find it without your equation, is what I think those kinds of questions will look like. They're not going to have you fill out a chart. Because you could just do that from here. Like if I give you the equation, you could just do it. I'd rather you do that, right? It's faster. But I'm assuming you will get a chart and you'll have to be able to read it without the graph. Without the equation. All right, so the limit of this graph as x approaches 4 from the left and the limit of this graph as x approaches 4 from the right are both 8. So if I didn't have the equation and I just look at this, look what's happening as we're going this way and this way. What number are you getting closer and closer to from both sides? Right, 7.9. Between 7.99 and 8.001 is 8. Questions? All right, example 4. This says use the graph of the rational function to find the following. So we go back to like function notation. F of 6, what does that mean? Good. Go to my graph where x is 6, which appears to be 6. We'll say it's 6, it's close enough. Okay, then I'm going to go to B. F of 2 is undefined. Good. The limit of my graph as x approaches -5 from the left is positive 2. Good. And the limit as x approaches -5 from the right, also 2. The limit of my graph as I approach 2 from the left, -infinity. As I approach 2 from the right, +infinity. The end behavior, the limit of my graph as x approaches -infinity, +infinity. As my graph approaches +infinity, +infinity. And domain. So domain goes left to right. What's my furthest left? Negative infinity. Does it stop at -5, where the hole is? Then it goes from -5 to 2, stops at the vertical asymptote, starts again at 2, and goes to positive infinity. No, because it can't include those. Questions on that one? All right. Now using the top one, okay? Remember, this is called that sign chart. It says positive, negative, undefined. We did this yesterday. Like, we got the graph and we filled in the sign chart. Now they're giving you the sign chart. So it says, which of the following must be true for the function f? So it's positive. If I had to actually draw this out, where would my zeros be? What happens at 0? There's either a vertical asymptote or a hole. We don't know yet, right? So there could be a vertical asymptote, but there could also be a hole. Now, if my graph is positive from 0 to negative infinity, it's above this graph, above the x-axis. It's negative, it's going to cross through, and then it becomes negative, or sorry, at 0, it's going to cross through, and then it becomes negative from -3 to 0. So if that's happening, now I assume it's going to be a vertical asymptote, not a hole, because it could just continue in the same direction. Then from 0 to 2, it is negative, so it's below my graph. At 2, it hits the graph, and from 2 to positive infinity, it's positive. So I assume it looks something like this. Again, I established it by starting with the zeros and then finding anywhere it's undefined. So if this is the case, A, it has a maximum at -3 and +2. Does it have to be true? No. It has a minimum at -3 and +2. No. It has exactly 2 distinct real zeros. It does have 2 distinct real zeros. It has exactly 3 distinct real zeros. No. The graph has a vertical asymptote at x equals 0. So what did we say could also happen there? It could also be a hole. So my graph can do something like this and just have a hole here. That's what it would look like, okay? So this is not a must. This is a must. All right, the next one, which of the following could be an expression for f of x? So think about what has to happen in the denominator. It has to be my either hole or vertical asymptote. So I either need to be able to cross through x in the top and the bottom, or I need to be able to cross through x, or I need x to be alone in the bottom. Well, if you look at them, this would cancel, this would cancel, this would cancel, this would cancel. So that all works. But which is the one that would give me a 0 at x equals -3 and x equals +2? Good. Which, that one, right? Because I need it to be -3 and +2. It would be x plus 3 and x minus 2. Questions? Yeah.
For the first question, when it asks for the real zeros, how do you know there's no imaginary? Well, it's not asking that, but how do you know there's no more zeros that we can't see?
Because it goes from negative infinity. So that's going to keep getting bigger. And to positive infinity, that's going to keep getting bigger. If it gave you a range there, like if it's cut off, you wouldn't be able to tell. Yeah. But because it says infinity and negative infinity, you're going to assume it's going to keep going. All right, example 6 now puts the stuff from yesterday together with the stuff from today. So domain, zeros, y-intercepts, asymptotes, holes, and graph. And I said it before, but I'll say it again. The most important part is that you're finding domain after you factor, but before you find a hole. So the very first thing you're going to do is factor, both numerator and denominator. These should both be x's. Dang it, I almost made it. X squared, and that times x minus 2 is my numerator. Denominator, factors of -18, that sum to +3. x plus 6, x minus 3. Already you can see, is there a hole? No. But before I even got to that point, I would figure out my domain from here. I'm going to say this cannot equal 0 and this cannot equal 0, because even if you cancel it out for a hole, you have to include that restriction. So even if I canceled through this after this part, I still have to include it in the initial restriction. So x cannot equal negative 6 and x cannot equal positive 3. So I'd go from negative infinity to negative 6 and negative 6 to positive 3 and 3 to positive infinity. So that's my domain. Now I would check for holes, and there are none, so you'll literally write none. And then I'll go vertical asymptotes, because that just means I set this now equal to 0. So x equals negative 6 and x equals positive 3. The zeros come from my numerator. So if I set this equal to 0 and this equal to 0, I get x equals 0 with a multiplicity of 2. And that's going to be important if we have to graph it. And then x equals 2. How do I find a y-intercept? Plug 0 in for x, and that's easier to do from my standard form instead of my factored form. So this would be 0, this would be 0, my numerator is 0, which means that whole thing's going to be 0. And it was also a 0 here. Is there a horizontal asymptote? Go back to your exponents, right? In the top and the bottom, what's the relationship? It's greater than. So is there a horizontal asymptote? No. Is there a slant asymptote? Yes. So I take my numerator and I divide it by the denominator. I can't use synthetic because my divisor is x squared. So I go x to the third plus 3x squared minus 18x. Change your signs. Negative 5x squared plus 18x plus 0. Minus 5. Negative 5x squared minus 15x plus 90. I don't worry about my denominator, my remainder, as long as this first column cancels out. And then this set equal to y is my slant asymptote. Good so far.
Wait, how do you know when to stop?
When I ignore the remainder, that last thing would be my remainder. So as long as the term that would be the same exponent as the one on the outside, as long as that one cancels, so that negative 5x squared and the x squared, 5x squared cancels, then what's left is my remainder and I don't need it. All right, now we're going to graph all the things. So my vertical asymptotes are at negative 6 and positive 3. And my slant asymptote is at y equals negative 5. So I'm going to my y-intercept of negative 5. And my slope is up 1 and over 1. With me so far? All right, so my zeros are at 0 and 2. And it should bounce at 0. This might look weird. Hang on. Well, let's do the outsides. So if there's obviously something happening on the inside, right? And then there has to be something happening in the crosshairs that can't cross through my vertical asymptote. So I either need to be in this corner and this corner, or I need to be in this corner and this corner. What's something you could use that would help you with that? Say again. Sure. What about something we already found? What would my zeros do? Like, what are the zeros of your graph?
0, 2.
Right, but what are they in general in a graph? X-intercepts. So if my x-intercepts do not include anything to where I just drew, right? If it's not going to cross through here and it's not going to cross through here, then I eliminate those from what my graph looks like. And I know it's going to go here, and I know it's going to go here. How can, or not there, because it doesn't have a y-intercept. Here. No, just kidding. This needs to extend. Here. Okay. How could I double check that? Plugging in points. So if I wanted to plug in a point like that is beyond I would plug in something beyond this asymptote, and I would plug in something beyond this asymptote. But your zeros, if it crosses through there, your zeros will be given there. So now I need to know what happens in between, and to do that, I can plug in points. So if I wanted to plug in, let's say I want to plug in like -2 and see what happens, I would plug it in. -2 to the third minus 2 to the times -2 to the second over -2 squared plus 3 times -2 minus 18.
We would do this all without a calculator?
Yeah, because you can't have a graphing calculator at that point. Yeah. So you'd get -8 minus 2 times 4 over, otherwise you would just graph it on the calculator. 4 minus 6 minus 18. Really, what I really just need to know here is it positive or negative? Because that's going to help me figure out where my sign goes. So -8 minus 8 over -2 minus 18, -20, -16 over -20 is positive 4/5. So that part is happening above my x-axis. So if it's coming up on the left and it's coming down on the right, it's taking on this shape. And remember, it can cross through the slant and it can cross through the horizontal. It cannot cross through your vertical asymptotes. So the hard part about this one is it is bouncing at the 0, but it's bouncing so slightly. Like, I wouldn't expect you to then go like this, but this is what's happening. And if you were to like plot one, you would find it. It does come up a little and come back down. So the multiplicity affects it that way. It's just that it's so small that you probably wouldn't find it if you were hand drawing this graph, okay? You would know it because the multiplicity is 2. So I know it does bounce, but without plugging in that 1, you wouldn't have it. Does that make sense? You wouldn't know exactly where it goes. If I plug in 1, I get 1 minus 2 over 1 plus 3 minus 18, -1 over 4 minus 18, -14, and it's 1/14. So that's how high it comes up. It's literally just 1/14, but it is above your x-axis, which is consistent with your multiplicity of 2. Yes?
Why did like the graph go through the
It can go through slant. The middle behavior. So a slant, also like a horizontal asymptote, impacts your end behavior. If there is something in the middle, it can cross through it. It doesn't always, but it can cross through it. So if it's a cubic function shape, usually, that's when it's causing that. So cubic function, right? So this is x to the third. That's when it's causing that shape, in the middle to take on that cubic shape, okay? If you only had, which I think we're gonna do one more. If you only had a vertical and a slant, there weren't 2 vertical, then you're looking for your corners. It's either here and here, or it's here and here. This one's really complicated because it had both vertical asymptotes, okay? So you won't graph on your quiz. You'll find all those parts, but you won't graph on your quiz, yeah.
Would it be wrong if, like, you don't graph the, like, this part of it?
Yeah, you'd need all of it.
Like even the part that's not on the.
It's not on this graph, but it is a part of your graph. Yep. She's asking, what if you left off this? That's obviously a huge part of that graph. You can't leave it off. You'd have to know to find that end if it's above or below. They're always opposite corners when there's that slant like that, so that should be relatively easier. At least you can pick. And the zeros should help you with something like that. But I think exam-wise, I don't know that you're going to have to, on your AP exam, actually graph anything by hand. I think it would be more of a multiple choice, and you'd be figuring out which one it is. But it also won't be with a calculator, so you'd have to know how to do that by hand.
Why do we plug in a -2?
Because we wanted to see what happened in between here.
You did a -1.
Sure. Yeah, the goal is to see if it's above or below the axis. That's all. All right, last one. Find domain, zeros, y-intercept, asymptotes, holes, and graph. So first thing we're going to do is factor. The top stays as is. The bottom, you can take out a 3x, and I get x plus 2. Before, and there is a hole, obviously, but before I find it, I'm finding domain. Not equal to 0, not equal to 0, and my domain, x cannot equal 0 or -2. So negative infinity to 0, 0 to -2, and -2 to positive infinity. Oh my word. You know, sometimes the brain's just not turned on. -2, -2, 0. I was just making sure you were paying attention. Good job. All right. Now, is there a hole? Yes, it's happening at x plus 2, which means there's a hole where x is -2. Good. And to find the y, I take my simplified function and I plug in -2. God bless you. So 1/3 times -2 is -1/6. Now go through the rest of those motions. Is there a vertical asymptote? Yes, there's still a variable in the denominator. This cannot equal 0, so then x would equal 0 for my vertical asymptote. We eliminated the one at -2, but there is still one at 0. Is there a horizontal asymptote? Where is it? Y equals 0 because the exponent in the top. Actually, sorry, I wouldn't look there. It's still the same, but I would look here. The x would be raised to the 0 power into the first here. It's still smaller than it. Okay. How about a y, or how about the 0? If I look at 1/3x, is there a 0?
Why is there raising the 0?
Because there is none.
Oh, there's.
Yeah.
There are no zeros.
There are no zeros. How about y-intercept?
No.
It would be 1/3 times 0, which is 1/0. So, no y-intercept. All right, now, vertical asymptote at y equals 0. Horizontal asymptote at x equals 0. So now it makes sense there's no y-intercept because it can't touch the y-axis, right? It can't touch it. So that makes sense. So there's really two options here. Either both this kind of graph might have two curves in the top or in the bottom, or it might be one in one corner, one in the other, or vice versa. One in this corner, one in this corner, okay? So those are the two typical types of graphs. But I do know there's a hole in -6 and -1, or sorry, -2 and -1/6. So there is a hole here, which tells me my graph is going to be down here. Because the graph connects through the hole. It's just that there's a hole there. So then again, that means I either have something here or I have something here. And how could I figure that out? Plug in a point, like plug in 1, make it easy. Plugging into my simplified function. So 1/3 times 1 is 1/3. And I'd go 1 and 1/3. And now I know my graph is here. Again, I'm not gonna have you graph on your quiz. It might happen on your test, but not on your quiz. But you would have to give me all those parts. So I did do like 1, 2 questions, 3 questions actually, where you have to give all the parts. Okay, yeah.
How do you find your asymptotes again?
After you simplify it, the vertical asymptote, you set the denominator equal to 0. So it's the opposite of your domain. So after we simplified it, this was my expression, or this, yeah, that was my function, right? So for the vertical asymptote, we set this equal to 0, and I got x equals 0. And then for the horizontal asymptotes, you're looking at the powers on the exponents in the top and the bottom. Yep, so there's no x in the top, which means it would be x to the 0 power up there. And 0 is less than 1, that's your n and m. So because the n is less than m, your horizontal asymptote is at y equals 0. Questions? All right, yep.
How would you know it's the top one and not the?
I plugged in.
Okay.
Yeah, you literally plug in and see if it's above the x-axis or below. Typically, something that is x squared takes on the behavior where they're both in the top and both in the bottom after you simplify. So when it's just x to the first, they are usually opposite, but I would always just plug in and check.
And the reason it can't be this one is because we failed the vertical line test, right?
Correct. Yeah, actually good. Yeah. Yeah.